Take a look at this digital landscape. For years, the traditional data center was built exactly like this, a sprawling collection of rigid, isolated switchers that required individual configuration and heavy manual oversight. This animated diagram illustrates the primary flaw of that legacy design. To prevent data from looping endlessly, engineers relied on spanning tree protocols. That meant intentionally shutting down half of your physical connections to block the loops, creating distinct bottlenecks across the system. And if two servers right next to each other needed to talk, their traffic had to travel all the way up to the top of the network tree to a central gateway, just to turn around and travel all the way back down. Engineers call this hairpinning, and it wastes massive amounts of time and bandwidth. Cisco Application-Centric Infrastructure, or ACI, was built to bypass those exact bottlenecks. It does this by projecting a highly convincing illusion. To any external device plugging in, the entire data center behaves as one single massive switch. Beneath that illusion is a very different physical reality. The hardware is actually arranged in an intelligent, routed spine and leaf topology, where every leaf switch connects to every spine switch. ACI uses this physical structure to resolve a decades-old tension. It allows data centers to preserve the close-quarters Layer 2 connections that older workloads demand, while delivering the massive active scalability of a modern Layer 3 routed network. To understand how ACI pulls this off, we have to look at the first core component of its forwarding engine, VXLAN encapsulation. This diagram shows how VXLAN acts as a decoupler. On the bottom layer, we have the routed Layer 3 physical underlay, the actual cables and switches. Hovering above it is a separate, logical Layer 2 overlay that creates a flat, direct connection between endpoints. Because of this overlay, workloads behave as if they have direct adjacency. They think they are plugged into the exact same switch. The logical network is untethered from the complex physical paths navigated by the shadow packets on the layer beneath it. With logical traffic encapsulated, ACI introduces its second mechanical advantage, equal-cost multipath routing, or ECMP. Instead of relying on spanning tree protocols to block physical links, ECMP keeps every single physical cable active, dynamically balancing traffic across all available paths simultaneously. By combining VXLAN and ECMP, the operational math changes. Network administrators no longer have to ask which link is currently blocked. They simply look at how the fabric is balancing the load and where the endpoint is currently located. There is a third component required to completely fix the legacy gridlock, and it involves rethinking the Layer 3 gateway. In a traditional setup, all external traffic must route through a single, centralized default gateway, creating a massive point of congestion as the network grows. This network map visualizes the ACI solution. The architecture takes that massive central gateway and shatters it, pushing dozens of smaller routing nodes directly down onto the leaf switches nearest the actual server endpoints. By distributing the gateway, hairpinning is eliminated. Packets emerging from a server instantly hit a localized routing node and head straight to their destination. They never make the long, unnecessary trip to the core of the network. Behind the scenes, a rich control plane is tracking every endpoint location. Protocols like ISIS and CoOP constantly communicate, orchestrating this decentralized map of endpoints so the gateways know exactly where to send the data. Because of this hidden coordination, routing steps away from being a manual per-switch task. It becomes an automated intelligence distributed evenly across the entire fabric. Operating a data center this efficient requires a steep learning curve. The network engineer has to let go of their oldest habits. If you try to operate ACI by thinking in terms of isolated per-switch VLANs or singular default gateway boxes, you will fight the architecture every step of the way. But if you adopt the fabric mindset, the reward is shown in the data. You achieve high-density path utilization across a scalable grid, where every available link carries its share of the load. This unified behavior creates a clean operational return on investment. Because the packet paths and distributed gateway behaviors are coordinated across the fabric, troubleshooting becomes highly predictable. Operators get the immense scale and redundant pathing of a modern routed network, while retaining the vital Layer 2 connectivity that legacy workloads demand. By leveraging VXLAN, active ECMP pathing, and distributed gateways, ACI packet forwarding takes a fragile web of individual switches and coordinates them into a single, highly efficient machine.